Hello, everyone. So I'm Mauro from the University of Palermo. So I recently joined, Palermo from the UK. So let me start thanking the organizer for the fantastic hospitality. It was beautiful. So I'm here to talk about the way we can mix. Thank you so much. Machine learning-based approaches to data processing and quantum dynamics to enhance the degree of control and the possibility of engineering quantum states in photonic platforms. So I'll mix together a bit of theoretical and experimental work. Of course, I don't do the experiments, so I'll try and give the due credit to people when it matters. But before digging into it, Matteo asked the speakers to give an overview of the various research lines at the respective groups. So this is what we do in Palermo. So we have a plethora of different activities, all centered on the control of quantum dynamics. I should have asked, can you hear me all right? I typically shout. Is that okay? Yeah. So we are basically working on a number of projects directed to the control of mesoscopic systems, in particular thermodynamic related question, to then address a more, somehow standard problems in quantum information and the foundations of quantum mechanics. We are interested in understanding how quantum plays with gravity and how the quantum to classical transition takes place. But there is also a more applied line of research that is interested in structured phononic bar, waveguide QED, and non-emission topology. Francesco Ciccarello is looking into that. Very recently, we have started working quite heavily on topics of quantum machine learning. I'll dig into that in a second. I'll start with a caveat. I don't believe in quantum machine learning. I don't think there is any quantum machine learning, but we will address that problem in a second. And all these activities are supported by a number of research projects funded by a number of funding bodies in Italy and in Europe. Okay, so what are we going to talk or address together in this talk in the next half an hour? So I'll start with a very quick introduction to machine learning for quantum physics, very pedestrian, so incredibly inappropriate, I would say, but giving me the ground, setting the ground to address machine learning for quantum state engineering, and then this exotic approach to machine learning, which is reservoir computing, and how reservoir computing can be extended to the quantum domain for property validation of quantum systems and processes. Okay, let's start with the dirty triad, quantum state engineering. So I'm going to replace the good, the bad, and the ugly with what is each of them in the context of state engineering. So the annoying part of quantum state engineering, which is you need time, right? So that engineering quantum states is a very time-consuming process, in the sense that you have to optimize your lab, your experimental platforms very, very accurately. That somehow brings about also the bad part of it, which is that it costs a lot of money. Right? So it's an expensive process to ensure high quality, high fidelity quantum states, especially when you scale up the dimension of the systems that you're interested in to the genuine multipartite setting. And the ugly bit is that it might not even work. Right? So you spent a lot of time, you spent a lot of money on it, or you managed to get big grants and deploy the resources to your quantum state engineering tasks, and then in the end, it might not even work as well as you would like it to work. And this plot is taken from Stefano is here. Yeah, Stefano is here. So from a paper of Stefano with Antonio Mandarino and Matteo Paris. I might forget someone, sorry for that. But that shows basically a specific example of how quantum state engineering might really fail, even when you guarantee a very high fidelity. So this plot shows basically the separability region between two harmonic oscillators prepared in squeezed thermal states. So I squeeze a thermal state here, squeeze a thermal state here, there is no entanglement. And when I fix the total energy of my system and the number of squeezed excitations that I have, which is this parameter beta, then this blue region or purple, I'm partially colorblind, I don't see the colors very well, states basically where you won't find any entangled state. And then for the very same energy and number fraction of squeezed state, excitations, then you start generating states, entangled states, actually states that have a very high fidelity, with a given entangled state. Okay, so an entangled state with this means, so with this number, with this fraction of squeezed excitations. What you see is that although your states are very, very close to the entangled state that you would like to generate, the overlap with the separability region is not only non-zero, but quite sizable. So even if you guarantee that your experimental setting has achieved a fidelity that is larger than 99%, well, by no means you are guaranteeing that your state has the property, the important quantum property that you would like to achieve. Right. So that takes me to what I want to address, which is how machine learning can be leveraged and deployed to maybe simplify the task of quantum state engineering and somehow mitigate the ugliness, the badness, and the annoying bits of the task itself. So, simple-minded person as I am, I work with bubbles, okay, so in diagrams. So this yellow bubble here is computer science, okay? Anything that you can fit into the umbrella of computer science. And in this corner, I'm putting artificial intelligence. Now, the term is abused, overabused, but let's try to make a little bit of clarity in the context that we are addressing. So what is artificial intelligence? Technically speaking, is the study of intelligent agents. Okay, so what does that mean? There are devices, entities that perceive the environment and act so as to maximize the chances of successfully achieving a goal. You look at this definition and it fits perfectly with a politician. Right? It's the very same that is what you would define as a politician. No? Now, one more corner, in this little corner here, in artificial intelligence, there is machine learning. And if you're interested in finding a definition of what machine learning is, then you are in trouble, because we don't have a very clear-cut definition of what machine learning is. We know what it does. It seeks patterns in empirical data without forcing a model on the data themselves. So what you do is that you don't drive your model through, you don't drive your analysis through a model, you drive it through the data. So it's a data-driven approach, not a model-driven approach. You don't force feed a model to understand the pattern that you're observing. You try to extract the pattern from the data themselves. The patterns are derived and learned from the data, and they are used, these patterns are used to make sense of previously unknown inputs. If you are really, really interested in a definition, then you have, of machine learning, you have to go back to the 1950s, where when Arthur Samuel, in a talk, so this is a transcription of a speech that he gave, defined machine learning as a field of study that gives computer the ability to learn without being explicitly programmed. And that gives the impression, not immediately, the sense of how this is a data-driven rather than a model-driven approach. Okay, now a lot of talking about machine learning and quantum. What is machine learning helping us with at this stage when you're interested in quantum-related stuff? It's helping with quantum chemistry, optimizing and speeding up the process of identifying new compounds, quantum material science, quantum information, certainly quantum statistical mechanics. And And if you really ask me what quantum machine learning means, I think it means nothing, because there is no quantum machine learning. There are two different approaches to the problem. There is a quantum for quantum, and there is a classical for quantum one. Then you talk to other people, Alessandro Ferraro, for instance, and he will come with a quantum, quantum for classical one, and we fight every time on that, because I don't think that is it's a right approach. Anyway, so what is the quantum for quantum approach? You develop quantum algorithms to solve problems of machine learning using resources, quantum resources. And this is a very difficult task. It's as difficult as basically coming up with a new quantum algorithm. So that's the same degree of complexity as quantum computation. What is classical for quantum, on the other hand, is the sort of simple thing that I do. No? You use well-established classical machine learning methods, and you run quantum problems more efficiently. So there are a lot of very low-bearing fruits that one can pick up using this classical for quantum approach, and I hope to be able to give you a couple of examples right now. So what we commonly intend or mean for quantum machine learning is this gray area here at the intersection between machine learning, properly meant, and quantum information processing. And now we see a couple of instances where this interplay, this connection of the two different approaches is really proof. And my focus will be really the bad, the annoying, and the ugly. So quantum state engineering and validation. Okay, credit. So this is work done together with the group of Fabio Sciarrino in Rome and Lorenzo Marrucci at Federico II University, collaborating with us when I was up in Belfast and with people in Milan now and in Palermo. Okay, so yeah, whatever I'm going to say is much better illustrated in this paper, so go and have a look if you're interested. And again, let's start with the basics. Very, very pedestrian, so everyone knows what I'm going to say. Walks, random walks. Okay, so I have a coin and I have a walker, and the coin up or down determines whether my walker moves right or left. And now what you know, and we know very, very well, is that I can take a quantum coin that can be both in up and down at the same time, so in a superposition of up and down, which will affect the motion of the walker in a very peculiar way. Okay, so the quantum coin is in an up spin state and the walker will move right, or in a down spin state and the walker stays where it is. Okay, I have a walk on a line from a step, so from position -n to n, discrete lattice, and I'll move according to a shift operator that looks like that. Don't worry, I have only a few equations, and this is one of the, say, nastier one. Okay, so what I have is that, it's the opposite. Okay, so if the spin state is down, then my particle moves, otherwise it stays, but the logic is exactly the same. You run this motion classically, and this is the probability that your walker occupies position n in a lattice of 200 positions. You run it quantumly, and you have these two peaks distribution. So your walker spreads across the possible positions much faster. The variance is a lot larger than what it is classically, and people had a lot of fun exploiting these dynamics to pinpoint the differences between quantum dynamics and classical. Great. We started from the very same concept, and what we did was mapping these walk into a spin n dynamics. Okay, so I have 2n plus 1, or 2n depending on parity of n, 2n possible, 2n plus 1 possible spin state of a spin n particle. And what I wonder is, can I engineer an arbitrary state of this spin n particle? Okay, which means, can I engineer an arbitrary quantum state of my walker on a line? And what we did was the following. We allowed for the coin to be prepared at every step of the motion of my particle in suitable states. Okay? So you can change the preparation of your coin every time you have to toss it. Yeah? So the coin is not always prepared in the same state. I arrange it in different states step by step. And the question is, can I understand which is the best possible preparation of my coin designed so that I achieve a target state of my walker? Make sense? So you tell me which is the quantum state of your spin and particle that you want to engineer, and then my problem is to find out which is the sequence of coin preparations that allows me to generate exactly that state. Does it make sense? It becomes an incredibly difficult problem as soon as n becomes very large. You have many parameters to arrange. So what we did was using machine learning, backtracking optimization machine learning methods to find out. No, we asked basically a neural network to determine for us which are the parameters of the coin transformation, the coin preparation, that allows us to determine the optimal, so the desired state. Of course, there is a final projection. The state of the walker and the coin is an entangled state in the end, right? So at every step of the dynamics, you want to separate the state of the coin from that of the walker. So in the end, there is a measurement that you have to perform, which is the measurement that you should perform so that you extract the right state of the spin and particle. Then using machine learning, you can do that and synthesize arbitrary qubit state, arbitrary spin and states. And that's exactly what Fabio Fiorino and his team did in Rome. They use the technology that they are mastering for controlling the dynamics of a quantum walker on a line. And that is engineered through the combined use of polarization and orbital angular momentum degrees of freedom of light. So they are able to control both the polarization and the orbital angular momentum of light through a sequence of elements, of optical elements. The key one, so the shift operator being a Q plate, what they call a Q plate, which is a device that allows them, an active device that allows them to entangle the polarization state and to left or right to the orbit, the angular momentum of the orbital angular momentum degree of freedom. So basically a Q plate realizes these transformations, rotations in the space of polarization and orbital angular momentum, entangling them and performing the shift operator that I need to perform to arrange my random loop. The rest is standard passive linear optics. You let the light field go through this sequence of transformations, and in the end you perform a measurement on the polarization degree of freedom, therefore engineering a state of your orbital angular momentum, which is my spin n. What we did was determining through our machine learning algorithms which are the parameters of the Q plate that have to be engineered, that have to be arranged so as to prepare a given state of my spin n particle. And these are instances of the sort of spin state that we have prepared. So in this sort of Poincare sphere, for a spin n with n equal to 5, we have been able to engineer some of the states that you see here at the antipodes of this Poincare sphere, on the poles and the equator of the Poincare sphere. With this sort of, now this is the engineer state, is the walk position, and you achieve basically the distribution, the sort of distribution that you were tasked to achieve. Fidelity is fantastic. So for a specific instance, we were able to get a fidelity larger than 94% with a very simple, with a very rough analysis, and there are perspective for extending the dimension of the walk by combining different modules of that quantum coin and shift operator. And now let's take a look at which sort of other opportunities you have when you mix machine learning and quantum dynamics. And a particular case that I want to address is that of reservoir computing. So that's a very well-established method for machine learning in classical approaches. So the idea is the following. Suppose I want to reconstruct the image, the input that I have here, classical input to start with. And this time, what I do is that I take a random reservoir, classical reservoir. So this is a set of random scatterers. Okay, they scatter information in a completely classical manner. Nothing is quantum in this. Okay, and what I do is that I feed pixels of information to the reservoir. This information is scattered across the elements of my network, and then I don't train anything. So this is the difference between a standard neural network, where you train the coupling between the way information is propagated across layers of my network. I just let the reservoir evolve naturally. I don't put my fingers on it. You give me the reservoir, I take it, I use it without optimizing anything. The only thing I do is that I train the weights at the end layer of my reservoir from which I acquire information. And I use this information so as to map the input information to an output one that in the end will tell me which is the image, the unknown image that I have fed at the input. How do I extend this approach to the quantum domain? There are two ways, basically, two routes. The first is to use quantum systems. So now my image, my information to reconstruct is quantum. Quantum is the state of a quantum system. The second way to extend it is to use a quantum reservoir. So this time allowing for quantum dynamics to take place within the reservoir. Again, completely untrained. What I do is that I then measure one layer, the output layer of my network, so some elements of my network. I acquire information through those elements, and then I use that information to map the input information to an output one through standard reached regression methods, so very standard approaches that will basically tell me build a transaction between input and output. And the output will be able to reconstruct the property of my inputs. Great. Now, at the experimental level, again, collaboration with the group of Fabio in Sapienza and collaboration with Alessandro Ferraro in Milan and my groups in Palermo and Belfast at that time. So what we did was, again, leverage the quantum walk dynamics that these guys are able to control in the lab. This time, the walker, so the orbital angular momentum, embodies my reservoir. Okay, so I don't control the state of my orbital angular momentum. I use it as the reservoir that is able to process the information on the polarization degree of freedom, which is the state or the system I'm interested in reconstructing the property. So I prepare an unknown state of polarization. I let it evolve with the orbital angular momentum, which is my quantum reservoir in a quantum mechanical manner. Then I extract information by measuring the orbital angular momentum, and I'm wondering, can I use the information that I acquire through these approaches to reconstruct the properties of polarization? In particular, I'm interested in basically characterizing the expectation value of Pauli operators for my single mode of polarization, okay? And reconstructing it through this quantum reservoir approach. And this plot shows you that as soon as I use a sufficiently large number of training states, right? So as soon as the training that I have to prepare in order to get the transduction function between input and output, and that number of training states is large enough, then the error that I associate with the estimate of my expectation values of Pauli operator drops down by orders of magnitude. So it becomes really, really small for some of them. So I'm able to reconstruct the expectation value of these operators without even knowing which is the state that have been prepared. So this is not tomography. I've not tomographed the state of polarization. I've reconstructed properties of it without even knowing which sort of state I am. The final thing, and the final thought, very trivial, is can I scale it up? So instead of looking at a single mode, can I look at properties of two polarization modes? right? So polarization states. So how about entanglement? Can I generate a random state, an unknown state of two polarization degrees of freedom, let them evolve through my quantum reservoir of orbital angular momentum states, and then be able to discern how much entanglement I had in the input state without even reconstructing the state itself. So it's property validation rather than state reconstruction in tomography. And we basically double the sort of approach that we had in the single mode approach. So each polarization mode goes through a quantum, an independent quantum walk with its own orbital angular momentum. In the end, we measure individually the two orbital angular momentum states, and we get information to reconstruct an entanglement witness. And these are the so-called confusion matrices that you get when you want to discern a property of in this sort of approach. So these diagrams are clear. Maria, okay. These diagrams should be clear. So, for instance, if I have sent a state with an expectation value of my entanglement witness that is negative, so there is entanglement, with 74% of probabilities, I will be able to discern it as entangled. Make sense? And my error will only be 25%. Yeah, that's what these diagrams are. So you are able to discern. Yeah, we are done. We are able to discern entangled states, the separate states, without reconstructing them through these random approaches, random dynamics with an untrained quantum reservoir. Okay, with that, I abuse the patience of the chair, and these are the guys that put the bread on our table. These are the guys that suffer my tantrums in Palermo. Thank you so much for your attention.
Okay, no perfect explanation. And it seems that clarity comes after confusion with an difference. Okay? Are you confident that it always comes? In the sense that in the case of the polarization, after some confusion, something happened, instead of what, but and then. But
so, Paolo, let me try to see if I understand your question right. So, for instance, Paolo is asking, am I sure that at some point, so the epiphany moment comes. So basically that there is a threshold in the number of training states that I use above which really the error drops down. The answer is yes. It always happens. The question that I might not be able to answer is what is the actual threshold. So that is really the plug and play part.
Because also logarithmic scale.
Absolutely. So, but there is a plus. So at the level of single modes, that's great. So you train with single mode states, that's cheap. You might say, I mean, you're cheating here. Because how are you training your reservoir? Do you have to feed in lots of entangled state and then to be able to reconstruct the properties, so the entangled properties of your unknown state? And the answer is that our training here happens with all separable states. So you don't have to train your network, your reservoir, with entangled states at all. So your reservoir, by knowing what a separable state looks like, your reservoir is able to discern a previously unknown entangled state, although it has been trained with separable states only. So the training is entirely cheap. And although you need to feed lots of states, that's done offline. And that's done with very, very inexpensive states to be prepared. Okay.
So when you say weakness, so is it more efficient to doesn't detect one time state with respect to the case where you're driving back to weakness right your own state?
Okay, performances are better. So the performance is better. The performance is even better than certain approaches that have been developed recently, which are called shadow tomography approaches. So they are basically sort of compressed tomography approach. So you are able to reconstruct the state of your system without even performing a complete tomography of the state that you. The point is that here I'm reconstructing the entanglement weakness without having to perform joint measurements for my system. And without having to adapt my measurement itself. So you know better than me, the experimentalist comes and asks you, okay, so what do I have to measure in order to reconstruct your entanglement weakness? And typically you come up with a list of, say, bilocal measurements whose correlator are then elements of your decomposition of the entanglement. I don't have to do that. It's a fixed measurement that perform. I fix the basis upon which I measure my orbital angular momentum. I don't change it. I don't have to rotate it as I should do it when reconstructing in a standard way my entanglement weakness. So it's a fixed measurement. All the power comes from the fact that these fixed basis reconstruction method has seen lots of states before and is able to discern separable from entanglement. Okay, so you pay the price of having to train lots of state at the input, but cheap states, but you also have the advantage of not having to adapt your measurement device. It's fixed. They didn't have to rotate anything at the measurement basis. My basis has not changed. So the reconstruction is comparable, sometimes better, the performance is better, comparable or better than the one with the standard approach. And there is an add-on. The add-on is that I don't have to repeat to rotate my basis.
There's some particular entanglement state which this program does not.
No, not at all. Not at all.
Just
We tried up and down, left and right. We tried this plan, at least on paper, and we didn't we couldn't identify a preferred subclass of states to be there.
if your measurement basis is fixed.
It's fixed, absolutely, yes.
The training of your network is based on new experimental data.
Absolutely so.
Would you do it with simulation?
Sure.
See.
Thank you for the question. It's a fantastic one. So these set, so we have plots like that in the paper where we show the comparison between what the prediction achieved in a simulated set of states, input states, and the comparison with what you get with actual experimental states. Okay, so and the performances are compared.
So you would train your systems,
Synthetic data.
and then.
Thank you so much.
Okay, thank you again.